So continue to the topic. Carbon dioxide removal is a product of a respiration of fish and other organisms in the production system, such as the bacteria in the biofilm. At low stocking densities, carbon dioxide is removed by the physical agitation and exposure of the water to air. For every gram of oxygen consumed, 1.38 grams of carbon dioxide is produced. Carbon dioxide obstructs the respiration of fish by reducing the capacity of the blood to transport oxygen through a physiological phenomenon known as a Bohr effect. Carbon dioxide also directly affects the overall system performance by increasing its pH, which can stress the fish in and inhibit the nitrifying bacteria in the biofilters. And carbon dioxide can be controlled by gas exchange in the downflow trickling tower or pack column aerator, similar to the downflow trickling tower used by the biofiltration. And the carbon dioxide concentration in culture waters will also be impacted by the alkalinity concentration of the water. Like example, for the specific pH value, carbon dioxide concentration is proportional to alkalinity concentration. So next is the monitoring and control. The need of continuous monitoring and control of critical operation such as water flow, tank water level, and oxygen concentration also become essential to prevent the catastrophic fish losses. It takes only one mistake to kill everything on your facility. For example, if a power failure occurred in a moderately stack of 60 kilograms per cubic meter, the warm water system oxygen levels could drop to stressful levels to approximately 60 minutes, and if highly stacked, to 120 kilograms per cubic meter in only 10 minutes. So today, continuous monitoring systems are commercially available and relatively reliable. All the alarms should be reported to the phone dialer to notify the staff both during and after working hours. The authors recommend 24-hour people coverage wherever possible. The monitoring and control system can be as simple as solenoid valve that automatically opens the oxygen supply line to aerate during the power failure. For most facilities, simple, fairly inexpensive monitoring auto-dialer systems are commercially available, which will monitor 8 or more switch inputs and automatically switch on backup system and dial out in emergency situation. And regular monitoring of other parameters that change slowly with time requires as well equip and maintain the water quality lab, like example that tests for ammonia, the nitrite and nitrate, and also the alkalinity, and etc. It doesn't have to be an elaborate expensive facility, but it needs to be an dedicated location with all support equipment for good laboratory practices. Next is the current system of the engineering design. There are several alternative solutions to each of the unit process utilized in intensive recirculation aquaculture system. So the important design questions that are determine what unit process to use to include the species to be produced, the stocking density, production capacity, and the sensitivity of the species to the water quality parameters such as the temperature, the dissolved oxygen and the ammonia nitrogen, the pH, and the carbon dioxide, which is the CO2. So next is the current system engineering design. There are several alternative solutions to each of the unit processes utilize an intensive recirculation aquaculture system. The important design questions that determine what unit processes to use include the species to be produced, the stocking density, production capacity, and the sensitivity of the species to the water quality parameters, such as the temperature, the dissolved oxygen, the ammonia, nitrogen, the pH, and the CO2. And numerous combination and permutation of the above unit processes have been implemented over the past decade. And although no one system design have become the standard, several combinations seem to work well together. For example, many large-scale commercial recirculation systems use some form of rotating microscreen filter for solids removal combined with a Cornell dual drain system. Although the microscreen filters have a higher capital cost, their ease of installation and operation make them economically attractive. Most biofiltration is now accomplished with either a moving bed bioreactor or the MBBR or some form of granular media filter, such as the downflow bed filter or the fluidized sand filter. The main advantage of the MBBR is the aeration and the degassing they provide, reducing aeration or the oxygenation requirements. Fluidized sand filters have the advantage of lower capital costs and smaller size, but higher operating costs. Next is the recirculation system design, which is the mass balance, loading rates, and the fish growths. All system designs should begin with a mathematically analysis of the system loadings. Water flow is the mechanism by which oxygen is transported into the fish culture vessels, and the waste products being generated within are removed. The design of the recirculating aquaculture system, the RAS, should ensure that the important parameters affecting the water quality and the fish productivity, like example, the oxygen, ammonia, and carbon dioxide and also the suspended solids, are properly balanced. So this requires calculating the required flow rates via the mass balance equation to maintain the water quality variables at or below or above in the case of oxygen. Their maximum tolerable or the design target values. So the maximum flow rates are used to maintain the constraining water quality parameter will be a higher than necessary for the others, which simply means these water quality parameters will be at the better values than the design target. So the mass balance approach simply comes down to balancing the transport in some parameter, the production of this particular parameter within the culture tank, and the transport out of the parameter. In the word of equation form, the transport in of x plus the production of x equals the transport out of the x. So take note that the production term can be negative, meaning the consumption of the certain component of the oxygen. Note that x does not be referred to a concentration of the small x, for example in the milligram per liter, but rather about the mass quantity of some stuff referred to as x in the word equation. For us, it can be assumed that the culture tank represents a completely well-mixed the tank and that the tank has reached a non-changing condition with respect to time or the steady-state conditions. So another way of representing the mass balance equation uses the product of the flow rate with the volume per unit time multiplied by the concentration with the mass over the volume, resulting in the mass per unit time, as for example the kilograms of oxygen per day and kilograms of the solids per day, and etc., neglecting the effects of the flow through the component, which should be considered if the system discharge per day is 1 volume or more, the mass balance equation in its simplest form, QC in plus P equals QC out. The C in and out, it is the concentration of the parameter X into and out of the culture tank mass per volume. So the Q it is the water that is recirculated, which is the mass per day. So the P is the production rate or the consumption, which is the negative, which is the mass per day. So next is the selecting tank values. The designer or the manager must choose design or target operating condition to calculate the mass balance. So these are the C values in the mass balance equation. So these design numbers are species dependent and are continually being refined for the RAS application. The minimum flow required to maintain the target values for the water quality, and then using the the largest minimum value found for all the different water quality variables. Will show how the sensitive the calculate flow rates are the value of selected for the design value. Next is the water treatment device. Each treatment box unit process is a system that improves the water quality of the water. The concentration of the particular water quality, the treatment device can be calculated by knowing the best treatment device could achieve and the treatment efficiency of the particular device being used. The treatment efficiency should be provided by the device supplier or the manufacturer. So the general mass balance equation applied to the treatment box determines the concentration of each particular water quality parameter, leaving the treatment device. The treatment device could be a biofilter, a CO2 striper, or a solid settling chamber. Each will have its own treatment efficiency for the particular water quality parameter it is the design to treat. So the water quality concentration, the C out leaving the treatment box is found by the using a mass balance analysis is to be the C out equals C in plus T over 100 times the C base minus Cn. So in this equation, T is the treatment efficiency, which is percent, and C base is the absolute best result obtainable by the treatment system. Example is the zero ammonia or the saturated oxygen and also the zero suspended solids. Take note that if the device is an oxygen addition unit, the C base term can be increased above the atmospheric concentration value for the oxygen by increasing the partial pressure above the atmospheric oxygen partial pressure in the device. So the four major water treatment variables, the number one is the oxygen. So the major reason most fish die is from lack of oxygen due to a lost water flow. So this is because the oxygen is consumed at a fairly high rate of the fish metabolism, and oxygen is transported by the water flow. Due to the low inherent concentration of oxygen, the high flow are required to the transport the required oxygen. Flows required to maintain the satisfactory oxygen level are generally controlling the flow rate parameter. The series of mass balance equation is to determine the most restrictive parameter. It is important to remember that not only do fish require oxygen, but also the biological filter, which is critically dependent upon the adequate oxygen levels to support the bacteria metabolism. So always measure the DO coming out of the biofilters, and if the concentration starts to approach with the 2.0 mg per liter, then take corrective action. Example, the increased flow rate through the biofilter by increasing the hydraulic loading rate on the filter, or add the oxygen prior to the flow entering the filter or within the filter itself. The production term for the oxygen is, so the P oxygen equals the negative 0.25 is for the feed consumed by the fish, and the negative 0.12 is the feed consumed by the nitrifying bacteria, and the negative 0.13 kilograms is by feed consumed by the heterotrophic bacteria. Can be as high as 0.5 and equals the 0.50 kilograms is the sum of above per feed for system. So next is the ammonia. Definitive values for the toxic levels of ammonia and the differentiation between the toxic, which is the NH3 form, and the supposed non-toxic is the NH4 positive, have not been precisely determined. The apparent toxicity of ammonia is extremely variable and depends on more than the mean of the maximum concentration of the ammonia. A good rule of thumb is the value of 1 milligram per liter for the total ammonia nitrogen, which the ton, for cool water, and 2 or 3 milligrams per liter for the warm water fish. And you should always check your tan target value by selection by assuming some pH of and the temperature that you intend to maintain, and C of your NH3 concentration will be exceed the 0.025 milligrams per liter value using the readily available ammonium pH temperature tables from the several texts. So next is the carbon dioxide. So carbon dioxide is an important but largely overlooked the water quality limiting parameters. Most systems were generally low densities, less than 40 kilograms per cubic meter, and relied on the aeration as the main means of the supplying oxygen. As a result, the natural stripping of CO2 that occurs when the using aeration system was no longer taking place. The CO2 production can be explicitly related to the oxygen consumption as the ratio of molecular weights of 44 per 32. The PCO2 equals the 1.375 times the P oxygen. So next is the suspended solids. The effective control of the solids generated in RAS is probably the most important task that must be accomplished to ensure the long-term successful operation of the RAS. So the quantity of the suspended solids, or the total suspended solids, the TSS generated per unit of the feed being fed, is estimated as the P solids equals the TSS and equals to 0.25 times the kilograms feed fed, which is the dry matter basis range of 0.20 to 0.40. So another is the nitrate nitrogen. The nitrate nitrogen is not considered in the mass balance equation to determine the maximum required flow rate. In saltwater system, to the nitrate should be considered. The nitrate nitrogen is the end product of the nitrification process, and in general, concentrations of the nitrate are not extremely adverse to the RAS quality. So the nitrogen is essentially conserved through the nitrification process. So nitrate nitrogen is relatively non-toxic to the freshwater fish, and as the such will not be influenced to the controlling flow rates in the system. So the summary of the four production term: So the P terms in the mass balance equation, P oxygen is the equals the negative 0.50 kilograms per feed consumption by the fish, and the PCO2 equals the 1.375 grams produced for each gram oxygen consumed. So the P tan is the F times PC times the 0.092 and equals, and then the P solids is the 0.25 times the kg fed, which is the dry matter basis range of 0.20 to 0.40. So predicting the fish growth, the production rate also defines the required fish feeding rate, which then in turn determines the waste generation loads, like example the ammonia, nitrogen, the carbon dioxide, and solids, and also the oxygen consumption rate. Based on this data, the most appropriate treatment system can be designed based on both water quality demands for the economics. So common way of defining the fish growth is based on the existing data sets of the production trial under the commercial stocking densities, feed rates, and also the water quality condition. So second way is the based upon the temperature unit approach, and some define the numbers of temperature units to create a unit growth rate such as centimeters per month. So as you can see in the figure, the above equation predicts the growth using the units of centimeter per month or the inches per month, and the T values are all in either the degree centigrade or the Fahrenheit for values for the various species. The growth equation is subject to the limitation that if T is greater than T max, then the calculate of the growth at T max. Note that the excessive temperatures will compromise growth and or the feed conversion. So next is the stocking density, the mass of fish that can be maintained in the tank, or more appropriately, the mass of the fish that can be maximally supported. We should probably call this term the harvest density, or the density that when reached will trigger an action by the fish manager to move the fish to their next stage or to be taken to market. The number of fish and their individual weight will define the feeding rates from which all other individual engineering components are designed. The maximum allowable or safe densities for fish stocking is primarily function of the fish size, species, and the characteristic of the rearing environment and the management skills. New growers should target about half of the densities recommended for the expert growers. For example, is the tilapia system for the new grower should probably be operated at the maximum densities of 50 kilograms per cubic meter rather than the 100 to 120 kilograms per cubic meter. So as the conclusion, so therefore the design and engineering of intensive recirculating aquaculture system has made significant progress over the past several decades. The system components have been designed and engineered especially for aquaculture, and are the fields tested and available from the several commercial sources. The system integration is just the beginning to be investigated to determine the optimal configuration of an overall system design based on the species, production levels, and the water quality requirements. Even with all the success and improvements, though it is still challenging to implement the managed recirculation system that are cost competitive with other less capital intensive productions strategies. So end of the presentation. So I hope you learned this video, and thank you for listening, and God bless everyone.